morning to you, Prof. Gunther Paul, and everyone. I am greatly honored as well as privileged this morning to introduce Prof. Paul to this academic forum. Prof. Gunther Paul is an ergonomist, currently working with the Australian Institute of Prof. Gunther Paul is an ergonomist, currently working with the Australian Institute for Tropical Health and Medicine at James Cook University, North Queensland, Australia. He holds a PhD in ergonomics and MPhil in control engineering. His research focuses on complex work system related issues such as health systems, respiratory health, human in the loop modeling, or musculoskeletal disorders. Prof. Gunther Paul is loved to introduce him as a traveler between countries, sciences, and physical and virtual worlds. While Gunther was born in Germany, he grew up in Belgium and acquired his first practical skills in United States. From 1993 to 98, he was a student of the eminent Prof. Walter Rummert, who is considered one of the fathers of modern ergonomic science in Darmstadt, one of the prestigious universities in Germany. After 10 years career in the automotive industry, he received a call to become a professor in University of South Australia, where he pioneered to develop a ergolab. Prof. Paul is an international leader in the field of ergonomics, having inaugurated Digital Human Modeling and Simulation Technical Committee for International Ergonomics Association in 2009, which he was chaired for well over 12 years. In this capacity, he has served on 32 government and conference boards. He has been called upon as a scientific assessor by Canadian, Swedish, Dutch, and Belgian national research agencies and has provided 25 public media appearances. Prof. Paul has supervised over 30 postgraduate student projects, mentored postdocs, and served as postgraduate research coordinator in 3 organizations between 2009 to 15. His numerous publications include major textbooks, Digital Human Modeling and Posturography, and Digital Human Modeling and Medicine. He has served as an editorial board member of several major international journals, including as editor-in-chief of the International Journal of Human Factors Modeling and Simulation from 2016 to 20. After a long voyage, Prof. Paul was eventually settled in regional Queensland, where he has established a company providing disability services, which has just recently been nominated as a finalist of the Australian Disability Services Award in the Best Regional or Rural Services Program category 2023. Prof. Gunther Paul, this forum is over to you now.
Dear Professor Weir-Kuhn, valued colleagues, thank you for the invite. I'm very honored for this opportunity to speak to the Open University of Sri Lanka Research Sessions 2023. My name is Gunther Paul. I am an adjunct professor at James Cook University in Australia and the director of Aussie Ergonomics, an OHS consultancy and rehabilitation engineering provider in Queensland. I will talk to you about the digital transformation in ergonomics. In my talk, I will focus on digital human modeling and what is called the digital twin. My talk will be structured into an introduction to the digital transformation, an introduction to ergonomics, and highlights across different industries where the digital transformation has occurred in ergonomics. I would have loved to travel to attend this forum in Sri Lanka, but sadly, it is a digital conference, an indicator of the digital transformation in our lives. My parents visited Sri Lanka in 1983, and I still have a very good memory of how much they loved their holiday. With reports of friendly people, great walks, mountaintop adventures, and spicy food that was not for Europeans. I've never been there, always wanted to go. The virtualization of this conference takes us straight to my first topic, the digital transformation, whatever that might be. The digital transformation has been a confusing term to me for quite a while, which is why I would like to shed some light on this concept from my perspective. According to Wikipedia, digital transformation is the process of adoption and implementation of digital technology by an organization in order to create new or modify existing products, services, and operations by the means of translating business processes into a digital format with the goal to increase value through innovation, invention, improved customer experience, and efficiency. Along the same tune, the Chartered Institute of Procurement and Supply defines the digital transformation as technological advancements to build an efficient digital business environment. The Boston Consulting Group, however, a notable player in big business, notes that only about 30% of companies navigate a digital transformation successfully and focus on building companies of the future that blend digital and human capabilities. It may seem that at least in the entertainment industry, the digital transformation has merely and to a good part led to an enigmatic confusion about what is reality and what is virtual. Let's take a look at Apple TV and what our digital companion Alexa has to say about it.
Alexa, are Apple TV screensaver images real?
From Droidred.com. The images on Apple TV screensavers are not real.
Other success stories of digital transformation can be found in the movie industry. A great example is the digital reproduction of Tintin, the famous works by Belgian cartoonist Georges Remy, well known under the pen name Hergé. Virtual humans can do so much more than real humans. Virtual scenes are so much more exciting. Is that Walden?
Generations have searched for it.
Snowy, look at this.
I would like to invite you to answer that question for yourself one day. What is the digital transformation for you, in your world, in your area of research? What are the potentials? What are the benefits? And what are the costs? I will now shed some light on this inquiry from my background and my perspective. I will not attempt to answer all these questions. Yet, in the first place, this leads to the question, who am I? I am an ergonomist, not economist. Many people confuse these two. Ergonomists are half and half people, and I might gladly say mostly glass half full people. We are half engineers and half health scientists, and the third half would be social scientists. For this reason, ergonomics is an interesting science. It is, by its very definition, a multidisciplinary science. But it's also a science that leaves some people wondering where they belong. I first studied electrical engineering and control engineering, and I was very unhappy with the lack of humanity in my studies. I did not see how I could ever be successful in this profession. Towards the end of my mandatory studies, I had some very few optional subjects to select from. One was called labor science, which seemingly had no connection at all to my previous 6 years of study. And it left me flabbergasted why it had been added to the catalogue. Even from the abstract, I had no idea what that subject was about. I had to take it to find out. One semester later, the direction of my life had changed 180 degrees, and I had found a purpose. Ergonomics means labor science. So let's have a quick look at what that means. The International Ergonomics Association defines ergonomics, or human factors, as the scientific discipline concerned with the understanding of interactions among humans and other elements of a system, and the profession that applies theory, principles, data, and methods to design in order to optimize human well-being, which is health, and overall system performance or productivity. The word ergonomics was born in 1857, defined by a Polish scientist in a journal article called The Outline of Ergonomics, Science of Work, based on a truth taken from the natural science. The rest is history. Most people in English-speaking countries these days still believe that ergonomics was invented in 1949 by Hywel Merrill, an English psychologist, but that is fake news. I will now put the spotlight on areas in ergonomics that have been affected by the digital transformation, and I will show examples of the digital transformation in different fields. We will call this digital transformation in ergonomics digital human modeling and the digital twin. Areas that I will cover are defense, retail and services, manufacturing, public health, respiratory and cardiovascular health, biomedicine, mobility biomechanics, and rehabilitation engineering. Before I move on, I do have to shed some light on the term digital twin though. The term appears to be used interchangeably, and there's no clear differentiation. When semantically analyzing 118 publications in the field, we found that digital twin and cyber physical systems are terms representing the same object, and they're mostly used by engineers and computer scientists. Ergonomists, though, historically tend to use the term digital twin, digital human modeling, with an increasing prevalence for the term digital twin representing modern and holistic human models. The selection of my examples seems to be an awkward and colorful collection, apparently making little sense. But then this may be because I don't seem to make sense. Have a look at my career pathway. Military officer, control engineer, academic research and ergonomics, product development and research engineer, IT enterprise systems management, manufacturing engineering project manager, professor, researcher, automotive product development, and researcher in respiratory health and biomedicine. And eventually, I'm now an entrepreneur in rehabilitation engineering. Long story short, while the examples of digital transformation provided each highlight a phase in my personal life, they offer a cross-section of the digital transformation in ergonomics with the aim to help you consider the digital transformation in your very own scientific field. This is not intended to be a cookbook, but rather a storybook, and I hope that you will enjoy interpreting the story for your own benefit. My first example is from the world of defense. The Santos human material has been provided by Professor Karim Abdel-Malek and his team from the University of Iowa. Santos is a predictive dynamics human modeling system with adjustable body size, body type, body mass, strength, and fatigue behavior. While Santos can be used to design or assess vehicles with their human occupant, the system is most valuable in assessing human capability. For the military, CentOS comes with a library of equipment and weapons which automatically connect with the digital human, supporting the study of various postures and transitions in the field in order to better understand the feasibility of personal protective gear and equipment design. Because CentOS is an inherently biomechanical system, the human model will then inform the user about postural stability issues under major loading conditions or forces acting on the soldier, permitting the informed modification of gear or adjustment of policies. The model predicts the human response to vibration, which is a common noise factor in vehicles operating in the field, and it predicts human interaction with a complex mechanical environment, permitting the package engineer of an engine compartment, for example, to determine whether the package is fit for servicing and maintenance, an aspect associated with design for assembly. Equally, in vehicle package engineering, the digital model informs the designer about seated postures and the feasibility of the package, which needs to consider arm reach to the steering wheel and hand controls and foot reach to the pedals. When designing a motorbike, rider reach to the handlebar and foot controls is paramount. Based on target points for hands and feet, CentOS automatically adjusts posture and computes the complete biomechanical kinematic chain based on its predictive dynamics kernel without any real-world information recorded. Once a digital human is placed into a package, the system returns ergonomic assessment information regarding digital human motions, effort, comfort, or energy expenditure, potentially looking inside the human body and metabolism for further evaluation. In a jet, helicopter, or tank cockpit environment, thermal loading is often significant and can severely impede human operator performance. In this example, we see the digital human operator adjusting air conditioning controls before the thermal environment changes. Thermal zones are then shown and represent human thermal comfort perception. Enabling redesign of ducts and outlets or system capacity to improve cooling performance. Vehicle ingress and egress is an important factor when determining vehicle comfort or performance in the military domain. Due to the complexity of the environment and the motion, the study of vehicle ingress-egress in a physical laboratory environment requires huge effort and time. Compared to this, the digital human is easily adjusted to various anthropometries or mobility and reliably predicts the task. While in a traditional application, CentOS may be used to design and investigate a cockpit layout for a multivariate user population, considering the so-called ergonomic design paradigm of including the 5th to the 95th percentile user characteristics, which may be body stature, body weight, or even hand force. More recent and advanced modeling includes external dynamic bodies, which can be attached to the digital human body. This cutting-edge example shows a soldier supported by a dynamic exoskeleton, and the digital model predicts the combined motion of the digital human and its associated digital exoskeleton. While human system integration may seem the most likely application for digital humans, surprisingly, the focus in the military for the use of CentOS has been rather in human resources, the design, optimization, and quantification of training, and the understanding and assessment of human abilities as shown in the stair climbing exercise. My last comment on CentOS is some key different capabilities. CentOS predicts biomechanical loads within the body and typical loading conditions. Digital human modeling systems simulations that allow us to predict what is and what is not physically possible when loading a selected soldier without a backpack, with a 90-kilogram backpack, or with a 100-kilogram backpack. The second domain where we have used a digital transformation which is somehow connected to the previous is retail and services. Dr. Femke Dankers from the University of Antwerp has contributed to the section. Make Human, an open source digital human project, forms the basis of this work. Yet, even though body volumes are fully adjustable in the system, Make Human only produces naked human models. When imported into Blender, another open source computer-aided engineering system, a digital human can be rigged, which means an articulated skeleton with its biomechanical properties gets connected to the volumetric digital human model. In Blender, the model can also be dressed, since it is parametric, and the dress will match the articulated human and its posture. To dress the digital human, primitives can be defined to assemble variations of clothes, such as different sleeves, legs, or necklines. Once such a library of clothing and a library of digital humans are defined, Blender can be programmed to automatically import those data, mesh the digital humans for various types of clothing, and calculate parameters which are important in public health, such as the body surface not covered by clothing, an important factor in sun protection, and the prevention of skin cancer. We all purchase clothes online these days that turn out a poor fit, sometimes after the first wash, but often even before. The Shavatar tool helps us to avoid such mistakes when selecting clothing from catalogs. Since sizes vary significantly between manufacturers, the online tool uses the same digital human to calculate body volumetric proportions and create an avatar that best represents the physical human based on very few anthropometric measurements. This avatar is then used to match a huge library of products from all major clothing manufacturers, providing exact guidance on the correct size for a specific product. The third area where we have transformed ergonomics is manufacturing. Materials for this example have been contributed by Michael Spitzel and IMK in Germany, representing the EMA Digital Human. IMK integrates the EMA digital human in a complete dynamic representation of the work system. Despite the complexity of such a digital model, the system provides the highest level of detail and remains manageable through predefined and adjustable motion primitives and a high-level task-based plain language programming interface. EMA is so far mostly used in the automotive industry. The digital human's most recent advances there involve human-robot collaboration or cobot systems, where a human worker in the physical assembly world shares tasks with one or more robots without physical shielding. Another advance is the harness assembly of flexible cable beams, which forms a computationally highly complex process. IMK's most significant achievement, however, may be the modeling of interlinked and interdependent work processes, providing for any possible type of what-if analysis. The digital fabric fully integrates the digital human into such processes and provides task load and task time analysis, common ergonomic assessments, which were previously only available in what is called corrective ergonomics, principally after issues had been identified in the work system. The modeling of interlinked work processes enables predictive or preventive ergonomics, a much better perspective for workers and their managers. The next area of interest in the digital transformation is public health. Material in this section has been kindly provided by Professor Lee from Handong University in Korea. Think COVID-19. Here we look at the matching of respiratory masks to the face, a task we've all been subjected to just very recently. Traditionally, a few sizes of masks were manufactured and made available on the shelf and selected for the professionals, by a specialist most likely. More likely than the opposite, they did not fit. Using digital human modeling technology, a head is scanned in space and post-processed, generating a large number of over 37,000 vertices in a finite element model. When filtered through a computationally optimized generic template model, the head model is reduced to slightly over 5,000 elements. The same is done for modeling the possible spatial interface occupied by a face mask, which can then be overlaid with the head. When optimized, the results of this process are shown for two subjects. Their finite element digital face model consists of no more than 810 vertices. A similar process is applied to the mask, based on only 12 reference points, which can be computationally modified and moved to represent various mask shapes or sizes. The complete variety of face masks covering the selected face can be simulated. When automatically simulating all these different mask shapes, the optimum pressure profile on the face can be determined from the finite element model, identifying the best mask fit. This mask shape can then be 3D printed to produce the best performing personalized mask interface. Which takes us to what happens next once aerosols have been inhaled. While we studied respiratory and cardiovascular health as a result of COVID-19, this work really started years before when investigating respiratory health of coal mine workers, a disease which is commonly referred to as black lung or coal worker pneumoconiosis. Those simulations have been provided by Hamid Reza Modus Avibeni from the Islamic Azad University in Iran. Here we're looking at the first 5 dichotomous generations of the bronchi from the trachea. In a model created from a patient scan, we inject aerosol particles into the respiratory tract and simulate airflow of those particles to study constrictions. At the top end further up in the respiratory tract, we see the deformation from airflow from the nasal cavity through the pharynx and larynx into the trachea, providing information about potential upper airway obstruction. Again, particles are injected into the model, and the analysis of particle mass concentrations throughout the upper airways indicates areas of significant particle deposition, which may potentially contribute to infections, occupational obstructive respiratory diseases, or oncological findings. At the other end of the lungs, we're now looking at the lung parenchyma and the alveoli, little air sacs where the exchange of oxygen and carbon dioxide takes place. A group of lung conditions known as chronic obstructive pulmonary disease, or COPD, is very common in minors, and it is caused by damage to the alveoli. First, we see the pressure in the final generations and alveoli when inhaling or breathing out. We then inject aerosols into the airflow and again visualize the settling of those aerosols in the alveoli flowing through the lungs. And the velocity flow lines of this airflow indicating airway resistance. Much of the ergonomic science is based on assessing work as a function of stress on our heart. Electrocardiography performed in ergonomics is simple though and uses a maximum of 5 leads. Many methods are based on relatively simple metabolic assumptions. Finite element modeling of the heart and the aortic arch is shown in this simulation with the left subclavian and carotid and the right brachiocephalic arteries provides much more detailed insight into heart deformation and stress. Also shown in the finite element perspective with its model vertices. When injecting blood cells into the aortic arch, we can then determine particle mass concentration, obstructions, and blood flow. Assuming heart and lungs are functioning well, the study of mobility, or often the lack thereof in static sitting work, adding to a sedentary lifestyle, has become a key focus for many ergonomists. As a consequence, mobility studies have been conducted in complex motion labs, mostly using camera systems and markers in extremely costly setups. Those physical experiments are very difficult to control. This material has been provided by Beatrix Ballester and Sandra Alemany-Matt from IBV and Move4D in Spain. The digital transformation allows us to conduct digital biomechanical studies. What you see is not a computer-generated avatar, as much as it resembles one. This indeed is a real 4D scan human. 4D scanning adds time and thus dynamic movement to a 3D object scan. While this represents a real human, it is also a complete digital human, availing itself to any form of digital study. We have now transgressed the barrier between a physical and a digital human. This 4-dimensional registration system has been developed by Sandra and her team. I'm sure you will soon see many more applications, with the system currently being more widely distributed to universities and industry. In the past, digitizing such a complex sequence of movement required ambitious motion capture with a large number of markers impeding motion and an enormous effort in post-processing this captured data, driving huge cost and time demands. It is yet to be seen how this quick and cost-efficient way of capturing motion and transforming it into a digital model will change our lives. The Anybody model has been contributed by Professor John Rasmussen and the Anybody technology team in Denmark. Based on a Dutch shoulder model and an unattached leg model to analyze cycling, Ford and Aalborg University jointly developed this model in the early 2000s to investigate our musculoskeletal body with the aim to predict biomechanical load and eventually comfort. Anybody models several hundred active muscles, tendons and ligaments, as well as joints and bones. This model uses so-called inverse kinematics, a biomechanical method based on the measurement of the motion of typically up to 60 location markers on the body. While measuring the trajectories of such markers required physical lab experiments and much effort in the past, the kinematics of the human body can now be determined entirely from a digital human, such as the Move4D scanned avatar. Hence, one digital human informs the other. Anybody is based on mathematical optimization theory to calculate internal and external forces in a vastly overdetermined mechanical system. Based on the selected optimization algorithm, muscle activation patterns will differ, enabling the prediction of different conditions such as fatigue. The level of muscle activation is presented through muscle bulging and coloring. Let me show you an example of how this is used in ergonomics. In 2011, we conducted studies on automotive ergonomics in a motion lab that I had built in Adelaide. This lab was unique in its instrumentation and capacity for full-sized vehicles. We captured the motion of subjects loading boxes into a vehicle boot and used the captured motion to drive the jacked digital human in real time, mirroring the activity for further study. At the time, we also interfaced Jack and Anybody to enable analysis beyond geometries and anthropometric considerations. So here we see Anybody loading a box into the boot and providing us with a view into the human body, its forces and stresses. It would be of great interest to understand those musculoskeletal stresses for a different vehicle design with a much lower loading height. Instead of having to experiment with another vehicle, Anybody allows us to simulate that condition with minimum effort, simply by changing a few motion drivers. Instead of relying on subjective and highly variable comfort assessments, we can now objectively determine the best design. What would be the impact if we had to twist our body to load the box into the boot? Have a look at the erector-spinae muscles and especially the lower back. Muscle strain increases heavily on the right-hand side across the obliques, the lower back, and all the way up to the all the way up to the right shoulder, resulting in a heavily asymmetric loading condition, prone to causing injury. Beyond product design, such simulations inform training and the creation of evidence-based occupational health and safety regulations, such as manual material handling limits. Finally, I would like to highlight the area of rehabilitation engineering. Wheelchair seating remains a major challenge, and many wheelchair-bound patients suffer from pressure ulcers due to a lack of mobility. Our digital humans, however, so far do not represent the conditions of disabled persons. They are entirely based on a healthy population. Even the biomechanical and skeletal structures in our models do not represent the mobility impaired. And while Anybody theoretically supports the definition of mobility impaired bodies, only little work has been done in this regard. In the absence of proper full body models for disability, we continue to work with partial digital humans like this Telvis thigh model from human body scans. finite element model of a sprung foam cushion simulates indentation with a human occupant and calculates seated pressure at the human seat interface. The following material has been delivered by Professor Gregor Hari from the University of Maribor in Slovenia. We're now taking a look at the digital human and prosthesis design, and you see here a historical development chart for leg prosthesis from left to right. Leg prosthesis consist of a liner in a transtibial socket, a pylon, and a foot. While 3D printed and thus more personalized prostheses exist, their fit and comfort depends on a selected material for 3D printing, such as PLA, polystyrene, or composites. The material determines mechanical properties of the prosthesis, which in turn are paramount for the dynamic behavior of the socket, reacting forces on the leg stump, and consequently quality of locomotion and comfort. Rather than the traditional trial and error approach, however, the digital human model allows us to investigate interference and fit of the liner and socket for defined loading conditions and at defined points of the gait cycle, such as heel strike and push-off. We can then quantify and visualize mechanical stresses in the prosthesis at the interface with the leg for those different points of time during gait. The same simulation is repeated here for the three optional 3D printed materials for push-off. We can see that at the anterior knee side, the mechanical deformation is 60% higher for the PLA printed prosthesis compared to the composite print. Relative deformation of the socket and liner is directly related to compressive stress and the pain pressure threshold. Clearly, a 3D printed cellular liner manages almost perfectly to reproduce the mechanical behavior and pain pressure threshold of human body soft tissue. Although much of the design of the prosthesis, and specifically the transtibial socket, has been achieved in a digital environment, my message to you is that the resulting product remains a physical property for a physical living human, an objective that we should never forget. Let me summarize my talk. I've introduced the notion of digital transformation as it applies to the science of ergonomics and provided digital human modeling and digital twin examples from various practice areas in ergonomics, showing where the digital transformation in ergonomics stands as of today, mentioning potentials and benefits. I'm concluding my talk with an invite to you to reflect on the digital transformation in your area of expertise, scholarship, and research. What are the potentials? What are the benefits? And importantly, what are the costs? Again, thank you for inviting me. It was a great pleasure talking to you today. I wish you all a successful completion of the Research Forum 2023.
Thank you very much, Professor Paul, for informative as well as inspirational session. I believe for sure audience got novel idea about digital transformation and ergonomics. I think they got idea about how we can amalgamate health and engineering for the betterment of mankind. I invite audience, if you have any clarification, you can do clarify with Professor Paul now.
very interesting presentation, and that's really a new area for us, especially in this area. Like the digital transformation is connecting the different disciplines that the health science and the engineering and the actually that I'm not an engineering person. So, but I'm very much interested to know about that new design how you go for the personalized device and things. So when it comes to so if I look at in the so you explain that in a deformation and it's like that. So yeah, maybe that focus on to the particular person that has the defect and all. But in the
way that when you try to boost the efficiency of a person, so how this biomechanics that can go with the to increase the efficiency, whether it will fit to everybody or it has to confine to only the person who has the deformation or any other device, for example, that you mentioned, that the face masks and things. So it has to go in that way, or whether it is applicable or any other future application is there, how we can, how this research and thing can fit into the application part in a generalized way to make it the person in a more efficient way, considering these human factors.
That's a very good question and a very good comment. Thank you very much. So, in fact, when we wrote the digital book, Digital Human Modeling in Medicine, one of the arguments was that this is a transfer from traditional population-based medicine to personalized medicine. So the digital twin really is the step into personalized medicine. And this applies to all these models. So if you look at the respiratory models, the lung models, they originate in scans of one single person. So the model is created for one person, simulation applies to one person. And obviously with the data, so there are mountains of data that have already been accumulated in very large databases. We can then average across models of different people, but initially this enables us to provide a personalized simulation. So
Yeah.
the idea there was to create a personal avatar or a digital twin of every single patient, every single person, and connect this digital twin to the health record so that simulations with such systems can support and inform medical practitioners. But in any applications, models range from personalized to averaged and population-based models.
Yeah, in future that, but I understood at the moment that goes with the personalized mechanical level. Is that, but when it goes to application model, then you have to look in a different human modeling and that address the complex issue.
Yeah, so if you inquire into mechanical parameters, mechanical properties of tissue, for example, obviously we can only work with generic assumptions. If you look at muscle stiffness, for example, or length of certain muscle fibers, which have to be modeled in those systems like anybody, those are derived from specimen quite often. Again, there are larger databases from many specimens, so there are fairly valid assumptions, but you're right, they may differ from person to person, and certainly if we look at disability, and not every assumption may apply to every person. So we still need to accept an error margin because it will be impossible to determine those biomechanical parameters for every person unless we conduct a lot of biomedical sampling, which obviously would cost a fortune.
Yeah, thank you very much. Very clear explanation. So that's a new event here for all of us, right? Thank you. Audience, if you have any questions, you can raise now.
Yeah, thank you, Professor, for a nice lecture. Now, when it comes to health and safety aspects, now if we take a large-scale factory, we have multiple, many number of people. So now when it comes to the health and safety aspects, is there a way of generalizing the movement of people? I mean, when it comes to different types of people, there are different characteristics. So, is there any common way of finding the stressors coming to their muscles? Like,
I didn't fully understand that question. So,
Nipun, you can ask again because it may be not clear for him.
yeah. Now you thank you for a nice presentation, Professor. Now if we consider factory where we have many people, now if we are making a specific model, how can we how can we apply it for different kinds of people? Is there a common way of applying?
okay, so there's maybe we've got to go back. So thank you very much. I now really get your concern. We've got to go back to how medicine originally developed, or biomechanics developed, or even ergonomics developed with anthropometry. So, it started with very few people being sampled and measured. And then in certain areas like anthropometry, large cohorts were funded and sampled, and some of them with over 100,000 people being measured into a database. And CSAR is one of those exercises where people were anthrometrically measured and scanned in large numbers across many countries. And so we find this in other areas of medicine in a very similar way. So starting from one patient to a certain method being applied, and then more data being gathered in hospitals and assembled and compiled into databases which allowed statistical inference and the creation of models. And basically, we're now assuming certain models apply to everybody with error margins. But yes, initially those models were based on very few people. And that's what we are recreating with the digital twin. We start with personal models, but the more personal models we create, the more we generate generic models, which are sort of standardized, and those standardized models will then provide specific error margins so that we can assume whether there's a risk or not applying those models. So an example in digital human modeling, the early digital human models were just based on anthropometric databases. There's nothing else, there's nothing personalized in those models. So they were wholly population science-based, really just bought the data from the database, for percentiles of dimensions into the model. Not every human could be represented with those models because not every human fits in the combination of percentile measurements into those model assumptions. So now with a 4D scan, we can actually represent a specific human that may have been impossible to produce in a digital representation before based on population assumptions and databases. So I hope this clarifies.
Thank you very much, sir. Okay.
Yeah. Audience, do you have any questions? If not, we can conclude the session. I think there may be no questions yet. Prof. Paul, thank you very much again for inspirational as well as informative session. I thank you for on behalf of the OURS 2023. Thank you very much.